Hello everyone. Today we will discuss about a PIT section with our math sections. First of all, here we can see that pin CS chip selection of a given 8253 and 8254 is activated by a binary address A7 to A2, which is 100101. Here are 6 ports, but we have to get the 8 ports, so we have put there A1 and A0 for our forms. So first question is to find the port address assigned to this 8253 and 54. Here the chip selection part or CS is 100110, which was given all the same for 4 inputs, and then the A1 and A0 we denoted as 00, 01, 10 and 11. From here, this port we can say that 00 is for counter 0, 01 is for counter 1, 10 is for counter 2, and 11 is for control register. So the port address are in the hexadecimal form, and those are 100101, which is for the 9, sorry, 1001, which is for 9, and 0100 stands for 4. Then 1001 stands for 9, and 0101 is for 5. Then 1001 is for 9, and 0110 is for 6. 1001 is for 9, and 0111 is for the 7. So those are the port address that could be happen in the port address assigning section of 8253 and 54. The second question is to find the configuration for 8253 and 54 if the control register is programmed as following. Break down the control words into section like as 00110110, which is given on the move AL 0011101110. We first need to take the input, then compare it with the table that we have seen before, the table of this section that we have discussed in this diagram. So we need to count this for this diagram. Now moving on, compare with the table 5.1, indicate the counter is 0 since the select counter is 00. Here we can see that the select counter is 0, so the counter is obviously 0. Then the read write logic. The read write logic is 1 1. That means the lower bits first, then the most significant bit. Now the mode selection. In the mode selection section we have 0 1 1, which is the mode 3. So the mode selection is mode 3, which is to square wave generator. So in mode we need to generate square waves, and finally at D0 position we have 0. That means that if finally binary counter is selected since D0 is 0. If it was 1, then the output could be BCD. Moving to the next. Here we have counter 0 for binary counter of mode 3 square wave to divide the clock 0 by the number 4282 in BCD. To program the counter 0 for mode 3, we have an input. We have here counter 0, so the last two bits are obviously 0. Always make 1 1 to the read write logic. Okay, that means it will read the least significant bit first, then the most significant bit. So we have declared 1 1 here, and now we have the mode is 3, so we need to write 0 1 1 for mode 3, and we also have the in the output we have to the BCD. So in D0 position we obviously have the 1. So for this control register we have this code move AL 37H is the hexadecimal form of this given input, where counter is 0, mode is 3, and the output is BCD. Then output is on the 97H port. We have counted this from this binary where the port is 97. How to count the port we have already discussed in this section number A. Now move AX4 to 82H is to load the divisor. Then the output 94AL is to send the low bits. AH is to count the 0 and 94AL, and then the high byte to the counter 0. Those configurations and code are very important for your exam question point of view. And then we have the same type of question in the B. Here we have counter 2 and the binary mode is 3 and the divisor is to C to 6A hexadecimal. Here we have counter 2 mode 3 and in binary we have hexadecimal. Then send it to the control register, load the divisor, send the lower bytes counter 2 and then send the higher bytes to counter 2. The question number C is very important to find the frequency of out 0 and out 2 in A and B if the clock 0 is 1.2 MHz and clock 2 equals to 1.8 MHz. The output frequency for out 0 is 1.2 MHz divided by 4282, which was given, in which by transforming this 4282 divided by 1.2 MHz we have the result 280. 1.2 MHz divided by 4282 results 280 Hz. And now moving to the next, here we have the clock speed is 1.8 MHz. So 1.8 MHz divided by 49770, which is generated by C26A in the hexadecimal form. If we convert it into decimal, we have 49770. So if we divided 1.8 megahertz by 4970, we could have the result of 36 Hz. Now moving to the next. This is also with the same type of example. You have to do it by your own at home. Here are the diagram of previous sections. This is nothing very much important, so we are skipping this. But in this section you need just to know that 40 to 43 are for the counters. 40 is for counter 0, counter 1, counter 2 and control register. Now here are some description of counter 0. You can go through them. Here D0 is for binary value and D3, D2 and D1 is for mode selection, and D4 and D5 is for read write, and D7 to D6 is for counter 0. We have already known that. Here are some description of counter 1. Using of counter 2. In the previous video we have skipped the DDR function. In DDR function we need to have double data rate. In the lower bit we have a data, in the higher section we also have a data. So we are sending two datas in the single line, so it is called DDR for double data rate. We are sending data on the upper side and also lower side, also upper side and also lower side. So this is called DDR. Now we are moving to the modes. Here is the mode 0, which is interrupt on terminal count. Here are some descriptions. In this mode, if the get input becomes low at the middle of this counter, then the counter will be stopped and the output will be low. This is the diagram for mode 0 operation. Mode 1 is for programmable one shot. This mode is also called the hardware triggable one shot. In this, triggable must be done through the get input by sending 0 to 1's pulse. This is the output diagram of mode 1 operation, which is one shot operation. Number 2 mode is to rate generator. In this mode, if the get equals to 1, then the output will be high. This is the diagram for mode 2 operation. Mode 3 square wave rate generator is the most important mode. In this mode, if the get equals to 1 and the out is a square wave where a high pulse is equals to the lower pulse if the n is a even number. So from this diagram we can see that we can firstly divided this output into two sections such as even numbers and odd numbers. If we have even numbers, that which is 4, so 4 will be divided by two parts. That means two parts will be two parts on the upper side and two parts on the lower side. And if the function is odd number like as 5, so firstly we will divided it, one part will be the 2 and one part will be the 3. So the 2 could be the lower or upper part and 3 is the another part which can be lower or upper. In this diagram we obviously can see that the clock pulse are going and moving on from 1 to 6. Here in the 6 is an even number, so we have two parts. In the 3 we have upper parts and from 4 to 6 we have the lower parts. And if it becomes the 5, so in first 2 we can be the upper or lower part, in the last 3 we can have the lower or upper parts. This is the most sequential operation of mode 3 operation. Mode 4 is for software trigger stopped. In this mode, if the gate is 1, then the output will be high upon loading the counter. The diagram will look like this. In mode 5, it is hardware stop. This mode is similar to mode 4 except the trigger must be done with the get input. This is the diagram of mode 5 operation. That's all for now. Thank you.